curve is at the cusp, which is a sharp point. So this is this example. So you can pause the video to write down take note. And after you're done, let's move on to the next example. So consider the curve defined by, sorry, not this one. So consider the curve defined by parametric equations x equals t cosine t, y equals t sine t over the interval negative pi from negative pi to pi. So I want you to find the equations of both tangents to the parametric curve at 0, at the point 0, pi over 2. So this time I want you to do the question on your own. You might want to pause the video to come up with a solution, and then after that we can discuss the solution together. So first let me give you a hint. So what I mean by both tangents at the same curve, it means that the t will have two solutions when x equal to 0. So after I give you a hint, off you go, and then okay, it seems that you found the solution. So let's go over it together. So we first find values of t which correspond to this point. At this point, t cosine t equals 0. Therefore, either t is 0 or cosine t is 0. When cosine t is 0, we have t equals positive negative pi over 2. But when t is 0, the corresponding point on the curve will be 0 and 0. But when t equals positive negative pi over 2, we have the corresponding point 0 and pi over 2. So we have the dy dt. Again, we need to find the three derivatives from the parametric equations. So dy dt equals sine t plus t cosine t. And dx dt would be cosine t minus t sine t. So therefore we have dy dx equals sine t plus t cosine t over cosine t minus t sine t. So when t equals positive pi over 2, dy dx will be 1 plus 0 over 0 minus pi over 2, which is negative 2 over pi. When t is negative pi over 2, we have dy dx as positive 2 over pi. So the equations of the tangents will be given by y minus pi over 2 equals either negative 2 over pi x or y minus pi over 2 equals positive 2 over pi x. So I'll give you a second to take note again. sorry, I'm wrote the opposite. It should be, this is 2 over pi, and this should be negative 2 over pi. Okay, so now let's move on to the next concept, area under the curve. So let's recall that the area under the curve y equals f of x, where a is more than or equal to x, more than or equal to b, and f of x is greater than 0, is given by the integral from a to b f of x dx. So in this parametric curve, so in the case of parametric equations, x equals ft squared, ft, and y equals gt over the interval alpha smaller than or equal to t smaller than or equal to beta. We have the area under the curve from the integral from a to alpha to beta gt times f prime t dt, or beta to alpha in terms of direction. Okay, so this is the equation we will be using to find the area under a parametric curve. So let's go over some examples. Maybe you want to take notes, so I'll wait for a second. Alright, so now let's go to the example. So the first one, find the area under the curve. X equals 2 cosine t, y equals 3 sine t over the interval from 0 to pi over 2. Okay. So first, let's put out the calculator, plug in the x and y in this case. So x, we have 2 cosine t. Y, we have 3 sine t. Okay, 3 sine t. Okay, so let's go to a window. We know that the interval is from 0 to pi over 2, so we have t minimum 0, t maximum we have 0.5 pi. Okay, and the x minimum we have 0, maximum maybe 10. Let's go y minimum 0, y maximum 10. Okay, let's see what will happen. So again, we've got this ugly curve, so there must be something wrong here. So let's go back to mode, radian. Okay, window. We have t minimum 0, t maximum. Or maybe we don't want to restrict the t interval. We just want from negative 50 to 50. Let's see what happens. You can see it becomes